Hi, this is Abhilash, and today we are going to solve another problem. So the problem is lead code 1192, critical connections in a network. So the question is, there are n servers numbered from 0 to n minus 1 connected by a unidirected server to server connections. So it's a graph, unidirected graph. So forming a network where connection I is denoted by AI, BI, where A and B are nodes. So the representation is a list. That means a list of edges. So any server can reach other servers directly or indirectly through the network. A critical connection is a connection that, if removed, will make some servers unable to reach some other server. Okay. So a critical connection is that particular server. If we remove that particular server or that connection or that edge specifically in the graph, then the graph becomes disconnected. Okay. So we have to return all the critical connections in any order. So in the figure that we see, we can see that 1 is connected to both 2 and 0. Similarly, for 0, it has 2 degrees, and for 2, it has 2 degrees. But the node 3, it has only 1 degree and one edge connection to 1. So if this link breaks, this signifies that this is no longer, all the servers are no longer connected. So this is kind of a bridge, we can say, which it connects to the other part of the subgraph. So to solve this problem, this is actually a problem of DFS. So to solve this problem, there are certain important observations. If we consider this graph to be undirected, so in that case, we have to see the visiting times of a particular node in the graph and also the time when it was discovered. So we have to consider two items. So one should be, since we are doing DFS, so DFS does that recursively. So the first thing is to check the visited time. That means the timestamp. So the discovered time, visited or the discovery time, better it is known like that. So to check the discovery time, which denotes the time at which that particular node was discovered. And we also have to check the discovery time as well as the lowest time. So the lowest time to reach a subgraph. So let's say the lowest time to reach 1 from 3 or any nodes of this subgraph starting from 1. So let's say the time or the lowest time taken for a traversal, DFS traversal, to go from 3 to 2 or 0. Also, this is an implementation which tries to use articulation points in graphs. So articulation points are those points which, if left disconnected, that means which if those are left disconnected from the graph, then the entire graph splits into different parts, into disjoint forests essentially. So we have to use that particular concept and DFS to solve this particular problem. So the approach will be to discuss the complexity first, because this may take some complexity. We have to use an adjacency list topic because we want to have a complexity of V plus E since we are doing DFS. So that should be taken into consideration. And also we have to see in the DFS, we have to keep track of two things. One is the discovery time and one is the lowest time for visiting a particular node. So once a node is visited, that means has been discovered, we will be checking whether the lowest time to reach that particular node exceeds the discovery time of its predecessor. So or of its ancestor. For example, let's say we start from 3, 0. So the node ID is 3 and the starting time is 0. So if we move to 1, the node ID, let's say, is 1 and the starting times becomes, let's say, 0 plus 1 equal to 1. Now if we see that the starting time, that is the lowest time to reach 1, which is 1, is greater than the time for discovery of the ancestor node, that is 3, or any ancestor node. So let's say the ancestor of 3, if this graph were to be a little bit bigger, in that case we would say that this is a strong like articulation point, or this particular edge is a bridge. So similarly, this should be one of the conditions. So once a node is visited or discovered, we have to check that the lowest time of that particular node should be greater than the discovery time or the visited time of its ancestors, of its ancestor, or of its parent, right? So this will only ensure that there is a bridge or a bridge connection in the graph. And the second most important thing is, let's say from 1 we traverse 1 unit of time and we go to 2. So in that case the id becomes 2 and the time becomes 1 plus 1 equal to 2. So and again by DFS from 2 it can go to 0. So here the id becomes 0 and the time becomes 2 plus 1 equal to 3. So from 3 it will again backtrack to 2, because from 3 it will find that it has a connecting node to 1. So it will check the minimum. So for the rest of the connected subgraphs rather, we have to check that the minimum of a node, of a particular node, should be equal to the minimum of its of the node, of the current node, the lowest value, minimum of the lowest value of the node, and the, let's say in that case, the other nodes, that means the lowest time of its children, So in that case, for rest of the subgraph components, since it will always form a cycle or it will always form a closed graph, we have to check the minimum of a node and assign it to be the value of the minimum lowest value between the node itself and the node of its lowest value of its children. So this will ensure this policy, like over here the id becomes 0 and the time becomes 3, but in this case it has a connection to 1, which is one of its ancestors, and here the value was 1, the time amount was 1. So instead of 3 it will get updated by 3 to 1. In the same way, backtracking through DFS, it will again go to 2, and here it will check for 2. It will update its value by checking from its ancestor, that is 0, and it will update. So initially 2 had a value of 2, lowest value of 2, and 0 has an updated lowest value of 1. So it will compare 2 and 1, which is the minimum value, and it will update that value here. So in this case, it will be 2, 1. So in the same way, 1, 1 is always there. So in this entire subgraph will always have a minimum time of 1. But this particular subgraph, which is a disjoint one, so in that case, the minimum time is 0, 3, 0, right? So this is the trick that we have to follow in this particular problem. So the first step is to create adjacency list. So for that, let us initialize an adjacency list. It will be having a dimension of n, that is the number of nodes. So let's say I less than connections dot size. So since we are given a kind of a list, I guess, so we can create this bidirectional adjacency list representation of the graph using this vectors. So let me copy this particular part, because since this is a bidirected or undirected graph, we will be having both the edges, right? So now, once we have created the graph, the next step is to create two vectors, right? So these two vectors are, what are these two vectors? The first is the discovery vector, and the second is the lowest vector. I would say the lowest time vector. Okay, so let me write this as vector of int. Let's write this as discovery. Discovery is a big name, so let's write it as disc n, -1. Right. So similarly, the lowest will be LOW, n. Since the lowest will not have any particular value at the start, so we can also initialize it with -1, but here I'm choosing not to. But the distance or the discovery value should be kept to -1 because we should be incrementing a time counter. So for that, let me also create a global time counter, right? So this will help me. And the next step is to create a DFS function, right? And for this, we have to create a function which iterates through each and every step. So for um, auto I equal to 0, I less than n I plus plus. So for each of the connections, it will iterate. And first it will check if the visited of a particular node, that means visited I equal to -1. So this indicates that, sorry, this is not visited, but rather discovery. So discovery of I equal to -1. So this indicates that node is unvisited at first, right? So this will indicate that the node is unvisited. Now I'm going to call a function which is DFS. This will be a void function. So in this case, I'm going to pass certain arguments. So ADJ list, that is the graph, will have to be passed first. So there, after that, we will be passing. We have to also create a result, since we have to return a result. So let me create a result in this case. Sorry, so this should be the result vector, right? Since we have to return a vector of vectors. Okay. Now we also have to pass the input as DISC and LOW, that is the discovery and the lowest time vectors. And we have to take two additional components, that is the current index I and the index of the parent. In this case, the I itself, because I is the starting point. So five, I would say 6 arguments are there. That is in a list, the resultant vector of vectors, the discovery time, lowest time vectors, the index, and its ancestor or its parent. So, and I'm going to return this particular. So this is completes my main function. So in this case, let us write the void DFS function. So in this case, let us rewrite the adjacency matrix, adjacency list rather. The next argument was the res value, so which is the output. That after that we have DISC. After that we have the low value or the lowest time value, and next we have the vertex, the current node or the current vertex, and after that we have the parent. Now once this is done, so let me write this as IDX, or rather U. Okay. So the first step in this function is to increment the timer or the time variable. So time plus plus, because at each step of DFS, we are incrementing the counters, even except in the in the backtracking stage. At each step, we are incrementing the count. So DISC of U will be equal to the low of U will be equal to time, because at the starting time, at the starting point of every DFS iteration or recursive call, we are going to update, we are going to increase the timer, and we're going to update both the discovery time as well as the lowest reachable time. So now we have to write the main function. So I iterate through the children. Children means the connections, not the connections of a particular node. So for that, for auto, let's rename this as V. Okay. So in V of adjacency list of U, so this tells us that it will iterate through all the nodes which are present in the adjacency list of U. And now we are going to check. First, we are going to check if V double equals to parent. So this check signifies that I'm going to do a continue over here, because I do not want to revisit the parent. If a parent is revisited, if a parent is visited, no need to revisit because that has already been completed. So we can just think of it like this way, that a particular parent, all the connections that are there, if a particular vertex after cycling back, let's say from 1 to 2, from 0 again, from 0 if it backtrack to 2, again backtrack to 1. So if we see 1 again, we will not be again considering it, so we are just continuing in that step. Or it can be done in a different manner as well. In other if conditions, we can specify if v not equal to parent, so same thing. So now the checking condition, that is the main logic that we wrote over here. Once the node is visited, we have to check that the lowest time of the node is greater than the discovery time of its ancestor. So for this, we are going to do two things. First, check whether it is discovered, like the discovery part of that particular node v is -1. That means the node has not been discovered yet. Okay, the node has not been discovered yet. For the first time it is seeing that node. Now in this case, we'll be doing two things. First, we'll be calling a DFS, right? Call the DFS. So the DFS will be called for this particular node that we have, result disc low v and its parent. So v's parent is u because it is present in the adjacency list representation of u. So v's parent is u. So this will call the DFS. Now, once the DFS is done for this particular node, we are going to find the minimum values. Minimum values between whom? Between the lowest of u, that is the ancestor, that means the minimum of the lowest of the ancestor, and the lowest of v, that is the current node. And we'll be assigning that to lowest of u. So we are assigning the parent, right, by the minimum lowest times of the parent and the children. So low of u will be min of low of u comma low v. So this is done. After this, we have to apply check if lowest of the v, that means lowest of the children, current children, that is, let's write it here as v, is greater than the discovery time of u, that is ancestor. Perfect condition, because we just saw over here only. So if initially 3 comma 0 and 1 comma 1, so 1 is greater than 0, so in that case this will become a bridge. So we can use that logic here itself. If our low of v, right, is greater than disc of u. So what does this indicate? This indicates a bridge. So now what will we do? We will just push those back in the result, because we have to identify all the bridges in any order. So in this case, we are taking the order as the ancestor as first, or the parent as first, followed by the child node. Okay. So after this is done, right, after this is done, we can write another function essentially. So there will be an else condition. So let's say an else condition. Why we need this else condition? We need this else condition because in this case 1 2 0, so 0 will be updating the minimum time. So initially 0 had a time of 3 in the forward pass of DFS. So it will be updating its time to the minimum time of 1, which is 1. So 1 comma 3, the minimum time is 1. So 0 will get updated time of 1. So in that case, we will be writing this as the lowest of u, that is the parent, right, will be the lowest time of, let's say, u, and the discovery time of its children, that is v. Quite obvious, because let's say the lowest time of u is 1 and the discovery time of 0, which is its child, is 3. So 3 and 1, the minimum will be 1. Applying this logic over there is equal to minimum of low comma u and discovery time. discovery time of V. Okay. Now this should be sufficient to run. We have also identified all other conditions. So if the low V is less than or equal to the discovery time of U, then we do not need to consider anything. This ensures that we keep the children of a subgraph updated with the lowest time possible. This particular part ensures that the lowest time is always kept. Okay. Now this is our function essentially. So after we have done this particular part and we have coded this and we have understood the logic, what is happening, so we can test this to make sure that everything is working. So first let us run the code on this sample test case. The answer should be 3,1 in our case, because we are first pushing the ancestor followed by its children, 3,1. So since the order is not mandatory in the output, as 3,1 is also accepted, ideally it should have been 3,1, because we are okay, so we are going from I equal to 0 to n. So in that case, I think 1,3 is the right answer, because we are incrementing it. So either way, we are taking the parent first and then followed by the children. So had there been 4 attached to 3, then if we disconnect the edge between 3 and 4, in that case, that would also have become a bridge. So 3,4 and 1,3 together would have been the answer, since we have to return all the critical connections. Now, if we submit this particular function, or if this logic, let us try to see what we get. I think this should work if there are no errors. And it seems to work for all the test cases. Now, before we move ahead with the topic, so this particular problem is very interesting because it uses the concept of DFS, and it also uses a concept of DFS on articulation points or bridges, points or joints or bridges. So this particular concept is very interesting. So to summarize what we have learned, so let's write the summary over here. So the summary is create an adjacency list. Okay, once we have created, we have to initialize two let's say vectors. One is the discovery vector, right, and the lowest time vector. So the discovery vector ensures the first time where a node is discovered, and the lowest time ensures what is the lowest time to reach, or let's say to when a node is visited when starting from a particular subgraph or starting from a particular parent node. So, and we keep two different items, that is the current index of the node, that is the current node actually, current vertex rather, and the let's say the parent of a particular node. So how do we do this? It is very important to follow this particular pattern, because this pattern can be used almost everywhere for any articulation or bridge based question. So the discovery, we will update a timer, right, both for discovery and the visited, let's say the lowest visited vectors. And after that, the next step is to iterate through DFS, right? Iterate through DFS. If the current node is not equals to parent, that means if the current node is parent, then no point continuing. So if it is not equals to its parent and if it is unvisited, then only we will check for the lowest of the parent and the lowest of its current children, right? And the next step is the checking step, which is very, very important and the crux of this. So lowest of the in our case the particular children node, that is the current node, should be greater than the discovery time, right? Discovery time of the ancestor. So ancestor or the parent in this case, right? So this is the most important logic of this particular question. Okay. And once this is done, then This indicates a bridge, the bridging logic. And the next part is understanding, updating the minimum lowest times for the subgraphs, subchildren or the subgraphs. This is done very simply by taking the lowest of a parent equal to the lowest of a parent followed by the discovery time of the children, right? Just like in the example that we saw over here. Here 0, 3 and 1 is 1. So 3 and 1, the minimum time is 1. Okay. So this is the entire concept behind this particular problem. We'll be solving more problems on these DFS and BFS based approaches. I hope you like this video and we'll be seeing you in the next one. Thank you.